All right, so let's see, who else are we waiting for? We had one more, if I recall right.
I believe Kanari.
She seems to be on.
Hello, I'm here. Good evening.
Hello.
Now I see you.
And I see Jonathan, but I thought there were 4 total. I can't recall now.
I haven't seen Jared all day. I know he's in the class. I don't know what might have come up.
I'll wait just a minute, then give him a chance to connect if he can make it, but otherwise it is being recorded and he can catch up later. So, right, so we have been talking about radiation, just kind of an overview and what you might reasonably expect a member of the general public essentially to know at a place you might work at later. So today let's look at sources of radiation and talk about a little bit of nuclear physics to understand where radiation is coming from or how it comes about. And then we'll look at the interaction of radiation and matter next time and how to simulate those rates and so on. I guess one thing I forgot was or ran out of time to do is to look at radiation units. So what are some units you may encounter while talking about radiation? We had RAM and RAD in the training material for the general employee training. but you probably heard about becquerels, and you probably heard about several other units. So every time there's some incident at a nuclear power plant or something like that, all of this comes up in the media. And so what units have you encountered and what are their definitions?
The unit dosage is used in radiation physics according to my knowledge.
So which unit again?
The dosage unit.
Right, so radiation dose, but what is the unit? So it's either rem, right? Or there is another unit.
I believe we talked about grays.
Right, so we haven't really talked about it, but gray is a unit. So, all right, so what are all of them? And how do they relate?
I have an equation from my book from last semester, but I don't know how to share that with you guys. It says 1 rad is equal to 0.01 gray, which is equal to it says 10 squared times 10 to the minus 4 joules per kilogram. But that doesn't make sense.
Joules per kilogram. All right, so not just energy, but energy per mass, right? So if you have a certain amount of energy and, oh, there's Jared, hello. So if you have a certain amount of energy, you also need to consider what volume it's spread out over. If I deposit, 1 joule of energy or whatever amount of energy spread out uniformly over my whole body, it's of course going to have less of an impact than if I deposit 1 joule just in my eyeball, right? Or just in, whatever, some small part of my body. And so that's radiation dose. Radiation dose is energy per mass. It doesn't take the density into account or volume, right? It's just per mass, right? So that's radiation dose in either gray or red. And as you said, 1 rad is 10 milligray, right? Or 1 gray is 100 rad. Okay. And so then there's this quality factor that takes into account the different types of radiation. And then we can convert from rad to rem or from gray to sievert. And so similarly to the relationship between gray and red, 1 sievert is 100 rem or 1 rem is 10 millisievert, right? So actually, let's see here. I guess yeah. So here, okay, this is just a website that was published soon after the Fukushima nuclear accident, after the tsunami. And so there's radiation dose metric and commonly used in the US. Equivalent dose for exposure, taking into account that different types of radiation have different quality factors. And then we also have a becquerel, which is 1 count per second. So that's an SI unit. But usually a radioactive source has an activity that's much higher. And so just like a more convenient unit is the ampere rather than 1 elementary charge per second, a more convenient unit for the number of decays in a radioactive sample is the Curie, which is 37 gigabecquerel, right? So these relate to the source. If you have a radioactive source, it has some activity, and a half-life later, it has half that activity. And if nobody is around to capture that radiation, the activity is the same as if somebody's standing right next to it, right? So radioactivity at the source, that's the number of decays per second. And then if those decays, if the radiation from those decays hits a person or even a piece of equipment, it can deposit energy, that's reds or grays. And if the material that's hit is human tissue or some animal or something, then Sievert and REM are relevant. So for X-rays and gamma rays, for electromagnetic showers, it's the same. The quality factor is 1. Neutrons have a factor of 5 to 20, depending on their energy level. So they do 5 to 20 times as much damage as the same amount of energy in X-rays or gamma rays. And then alpha particles can do 20 times as much damage, but only if they get into your system. So alpha particles, as we are going to discuss, are very easy to shield with just a piece of paper or something. They are very large particles, right? Nuclei of helium atoms. And so they can't penetrate through even a very small amount of shielding. And so alpha radiators are not dangerous if they stay outside your body. But if it's a gas or if you inhale it and the alpha radiation comes about inside your body, right where it can hit cell nuclei and cause mutations, then it's very dangerous, right? Okay. So those are the most common units. So there's 3 different concepts. Decay at the source, energy absorbed, and the effect that energy absorbed has. And each of these 3 come in an SI variety, Gray, Sievert, Becquerel, and in a variety that's been historically used and is, giving more smaller numbers. Instead of dealing with gigabecquerels, we can deal with 1 Curie of activity, right? Things like that. All right, so that just to finish off what we had already talked about a little bit. And so, all right, so I want to discuss today just a little bit about what produces radiation. And we know to first order that's nuclear interactions, right? Nuclei decaying or something like that. So what do you think is relevant? How do we approach this? What do we need to describe if a nucleus is stable or not?
presumably we would want like a half-life to describe stability of nuclei, either as like a small half-life means that it's very unstable, long half-life means that it's very stable, and an infinite half-life would mean that it is actually stable.
Okay, but that now means we have so a nucleus is any number of protons and any number of neutrons put together, right? Not all combinations are stable. Some never form stable nuclei, right? If I have just 5 protons and no neutrons, it just won't come together, no matter how hard I push. But even if I restrict myself to just the periodic table of elements and just the isotopes of each element that actually are stable, that's many hundred different nuclei. And so now I have a table of many hundred different numbers, and I don't know why a particular combination exists or doesn't exist, right? So that's, that's really just kind of casting it into a different language, right? So what can I do to I guess, reduce the complexity, or, find fewer numbers to explain what's going on?
About the binding energy.
Right, exactly. So maybe you have talked about that. All right. So just let's take the bottom-up approach, and I don't want to talk about history too much, but so there, atoms were discovered, right? Rutherford did the experiments to shoot alpha particles through a small gold foil and basically prove that most of the matter of an atom is concentrated in a very small volume, and the light electrons take up most of the space, right? So the nucleus exists as a positively charged entity at the center of an atom, and the electrons are around the outside. Then, Niels Bohr came up with the Bohr model, which successfully explained a lot of the spectroscopy we observed and could reproduce, Rydberg formula and spectra. And then we developed quantum mechanics, and we can solve the Schrödinger equation for just a point potential representing the nucleus and derive all the properties of the periodic table, right? But from that, we just know that nuclei with a certain number of protons exist, right? Anything from 1 for hydrogen to, fairly large numbers, right? Anyway, just unstable nuclei much higher. Lead 82 protons, right? Bismuth 83, and so on. Uranium 92 protons, right? And so why are those nuclei stable? And then also we observe that there are different masses for the nuclei, different numbers of neutrons can be attached to that number of protons that makes up every element. And for hydrogen, it can either be a proton or a proton and a neutron, making a deuteron, or a proton and 2 neutrons, making a triton, right? And similarly, for many other nuclei, we have many other isotopes with different numbers of neutrons. Okay, so we know the nucleus is tiny. We know it's not point-like. Even with Rutherford-like experiments, we can scatter, and if the alpha particle remains outside the nucleus, the simple scattering formula follows the what we would expect. But if the alpha particle has enough energy to penetrate the nuclear material, then the effective charge after it penetrates is just the charge enclosed in the smaller sphere, right? Depending on how deep it penetrates. And the scattering angle will deviate from what simple derivation based on Coulomb repulsion would tell us. So we know the size of nuclei, and we know that roughly, also based on nuclear mass, nuclei are made up out of a certain number of protons and neutrons. And so what's the model? How can we come up with the model for the nucleus? So it's called the liquid drop model, right? You have a bunch of nucleons. So protons and neutrons together are called nucleons. They appear very different at the surface, right? One is positively charged, the proton. One is neutral, electrically neutral, the neutron. But then again, they have almost the same mass. They have a substructure made of 3 quarks each, and so on. And so really, well, for reasons I don't want to go into, we call them collectively nucleons. And so we have these nucleons, and just think of them as little balls. And you might feel like they just shouldn't stick together, right? Because all the protons, of course, repel each other. So how come they can be this close together? So clearly there must be some other force that makes them stick together, right? We call that the strong nuclear force. Okay, so let me just share the screen. And okay, so we have, some neutron and proton and, many, many, many of them. Right? Some of them are protons, some are neutrons, and so on. Fill the entire space. And so there's the clearly there's the Coulomb repulsion between the protons, right? That would argue they aren't going to ever stick together, but nucleons exist because atoms exist because we exist. So there must be some attractive force, right? So this is repulsive. And so calling both protons and neutrons nucleons, there must be some attractive force between any two of them. And so if one of them has nearest neighbors in every direction, right? If it's in the middle, in other words, then there's a volume term. And that's positive, and that's the one that's going to explain why nucleons are possible. So let's, this model was initially developed by Carl Friedrich von Weizsäcker and others in the early 1930s. And a lot of what we know now was not known then. So actually, it's the semi-empirical mass formula, because it, with very few parameters, explains most of the nuclear properties. I want to just briefly explain where this is coming from. So we know the strong nuclear force now. It's basically when we have two quarks, they can exchange a gluon, say a quark and an anti-quark, and that can couple to a different quark pair. Okay, and that's the at a quark level what's going on. Now, protons are made of two up and a down quark, and neutrons are made up of one up and two down quarks, and they have these gluons going back and forth between them, if you like. But so you can then see that the up quark has a charge of plus 2/3 of an elementary unit of electric charge, and the down quark has a minus 1/3 of a unit of electric charge. Hence, plus 2/3 minus 1/3 minus 1/3 is 0 for the neutron, and plus 2/3 plus 2/3, 1 and 1/3 minus 1/3 plus 1 electric charge units for the proton, right? And it turns out we can never observe free quarks, and so these fractional charges aren't really going to appear on their own, but quarks do have those fractional charges. This is what the strong force looks like between quarks, and or also gluons themselves carry this color charge of the strong force, and you can have gluons coupled to other gluons. Anyway, this is important, but really for our formation of nuclei, what we want, there's also particles, for example, an up and a d bar, that would have plus 2/3, right? And then a bar means an antiparticle, plus 2/3, and then instead of minus 1/3 for the down quark, it's also plus 1/3. And so this also has a unit of plus 1, and it's called a positive pi meson. Okay, we could also have pi minus, which would be a u bar d, a quark and an anti-quark, and we could have a pi naught, which, let me just write it as u bar or d bar. That's not strictly accurate, but just anyway, you see it's matter and the same type of antimatter, so this annihilates very, very quickly. But these charged beasts, they can be around longer. And so I can exchange those pions between protons and neutrons, and that virtual pion exchange, that's what's causing the attractive strong force. So the strong nuclear force by meson exchange. Pions are one type of meson, medium heavy particles, meson, whereas the particles of made of 3 quarks are hadrons, heavy particles. All right, and so we have this volume term. So again, this, I just want to tie all the things you may have learned about here or there or read on your own together, right? So we have this volume term. Okay, but what about particle at the surface? It still is happy on this side, but not to the outside, right? So those that are on the surface have a penalty for not having all the neighbors they would like to have, right? And so that's like the surface tension negative. It helps to be able to write while standing close to the board. So there's a surface term that takes into account that not all the nuclei have nearest neighbors to in every direction, right? And again, we now understand what's causing this force, but even without knowing anything, just because nuclei exist, you can start writing down this model, right? Then you can just, measure what nuclei are stable and which ones are not, and which ones are tightly bound and which ones are not so tightly bound. And you realize maybe you need a couple of other terms to really make it work out nicely. So those other terms, they initially came about purely empirically, but we understand them now. Right? Empirical just because they explained data without having a theoretical foundation to really understand it, but now understood. So we have those 3 terms, and then there's a couple more. Let me, come on, close this. Let me actually be lazy here and talk about the other 3 terms just using a readily available resource, namely Wikipedia, because it's actually accurate and not all that bad. So there we are. We have the volume term, attractive due to nearest neighbors. We have the surface term that penalizes nuclei that are near the surface. We have the Coulomb term that's repulsive because there are too many protons in too small a volume, right? It turns out there are 2 other terms. One is an asymmetry term. If there's a neutron excess, and usually we have a neutron excess because the protons repel, and so yes, they contribute to this helpful volume term, but they also contribute to this bad Coulomb term, right? That makes it harder to force them together. Whereas the neutrons contribute to the volume term and not to the Coulomb term, so we end up with more neutrons. But there is an asymmetry term that's due to the Pauli exclusion principle, and so I can have energy levels for protons and neutrons filled up, and then if I have a neutron excess, I need to fill those up higher, rather than if I have the same total number of protons plus neutrons, but I have equal numbers of each, that's overall energetically favorable. But the asymmetry term, although it penalizes against large asymmetries, we still have usually a neutron excess in heavy and large nuclei. And then furthermore, there's a pairing term just because of the spin interaction. 2 protons like to pair up and 2 neutrons like to pair up. And so I can have even nuclei where all the protons have a partner and all the neutrons have a partner. Or I can have even odd nuclei where I have an even number of protons and an odd number of neutrons, or vice versa. Or I could have what's shown here, an odd nucleus that's got an odd number of protons and hence 1 left over, and an odd number of neutrons and hence 1 left over, right? Okay, and so with those 5 terms, we then just write down the expected behavior for each term, and we come out with one equation for the binding energy for the nucleus. So I should first of all explain the concept of binding energy. We know Einstein's relationship that mass is a form of energy, E equals mc squared. And so to know the total mass of a nucleus, if it's a stable nucleus, then it's equal to the mass of all its constituents. We have z protons, z times the mass of an individual proton, and n neutrons. So add to the total mass of the protons, the total mass of the neutrons. And now it turns out if it's a stable nucleus, then it's got some binding energy that's released, okay? So think about the Earth in the gravitational potential of the sun. It's a bound system. The Earth is bound to the sun. And if you wanted to take the Earth away and move it out to infinity, away from the sun, you would need to provide energy, right? Conversely, if you had the sun and a planet Earth way far away and you moved it in and started it orbiting around the sun, you would gain energy. Gravitational potential energy would be freed up by bringing the Earth close to the sun, right? Similarly, if you have, say, 2 protons and 2 neutrons and they are all far away from each other, and then you push them together, well, you can't do this, just by pushing gently, because the protons will repel each other because the nuclear force is very short range. But if you overcome that repulsion and you manage to bring them really close to one another, then energy is released from the system as it's forming an alpha particle. Makes sense? So that energy, that's the binding energy of the bound system, right? And so it's energy that's released, and hence the mass of a nucleus is less than the mass of all its constituents. It's less by the binding energy converted into mass units. Can I see a thumbs up or something from everybody? Does this make sense? All right.
Yes.
Okay. All right. So then I want this equation to calculate the binding energy, right? And so the volume term is just proportional to the volume, which is given basically by the total number of nucleons, number of neutrons plus number of protons. If I have an object with a volume A, then the surface area is that volume to the power 2/3, right? Cubic meters, cube rooted, squared gives me square meters, right? It's and so each of those has then some coefficient I can determine from experiment, from data. Then I have the Coulomb term. Well, what does that look like? We know that each nucleus repels, any one of them repels each of the other ones, right? So if I have one of them, it repels Z-1 other nuclei, and each one does that, so it's Z times Z-1. And then I divide by the characteristic distance between any two of them. And if and the cube root of A is the diameter of this, right? So it's a characteristic length, right? You might put in a factor of 1/2 because some of them are closer together and some of them are further apart, but that just gets absorbed in a constant anyway, right? So a characteristic distance, they are apart, and what the charges are, right? It's just each has a charge E and how many pairs of protons are there. And then the asymmetry term, that just depends on if I have how many more neutrons and protons do I have. And it again is normalized by the volume. It goes actually as the difference squared. And then there's this term for even, odd, or odd, odd. Odd, odd is penalized with this being one number. Even, odd, or odd, even, this term is just 0. And even, it's a negative term. Okay, so it's really a simple model, but if we fit, so we can go through each term in more detail, but I hope I've explained them sufficiently. So if we do this, we can then fit these coefficients, and again, it's a small number of coefficients. It's not hundreds of numbers of half-life. It's only a small number of coefficients, and they have magnitudes of tens of MeV. So I think we mentioned last time that the scale of chemistry is a couple of electron volts. The scale of nuclear reactions is 1,000,000 times stronger, mega electron volts. So the strong force is in fact strong, and by comparison, the Coulomb force is in fact weak, right? This coefficient for the Coulomb force, that's only 0.7. And so we have a small number of coefficients there, and you can do a least squares fit to the data, or never mind the different models here. For the level of detail I'm interested in, 13 and 7.8 and 17.8 and 18.3, it's details, right? So we get this model, and it's really rather successful. So it can we can then, for any number of neutrons and protons, we can calculate what is the binding energy. And what we get is this plot that shows us binding energies of up to 8 about a bit more than 8 mega electron volts per nucleon. Okay. All right. And then, of course, for very many neutrons and no protons, that's not a possible thing. There's zero binding energy. That doesn't stick together. And having lots of protons and no neutrons, the Coulomb repulsion dominates, and that also doesn't stick together, right? Here it's the asymmetry term that in the equation that prevents it. And so with just a few numbers, we really observe, we really derive what we can observe. So how good is the semi-empirical mass formula? Here again, the plot with number of neutrons and number of protons. And what's shown here is the difference in the observed binding energy measured minus what the simple semi-empirical mass formula predicts. And so a zero means we are spot on. A negative number means the a discrepancy one way, and a positive number means a discrepancy the other way. The semi-empirical mass formula was improved upon by Maria Göpert-Meyer's shell model of the nucleus. And so it turns out these nucleons, much like the electrons in the atom, the nucleons in the nuclei can form shells. And that's what explains these magic numbers we find in the nuclear structure, where especially the double magic nuclei have a larger binding energy and are more stable than what the semi-empirical mass formula predicts. But remember the scale. The total binding energy was something up to 8 MeV per nucleon. And the scale here is 0.15 MeV per nucleon, right? So we are off by just 0.15 in 8. Well, that's for such a simple model as the semi-empirical mass formula, it's really amazingly successful, right? Again, I'm not saying it captures everything that's going on in nuclear physics, far from it, but it does allow us to produce a graph of the nuclear binding energy. And so if I plot this binding energy just as a function of the number of nucleons, so now plotted as a function of A, okay, Z plus N. Of course, we've seen it matters if I have, if that given A is due to more or fewer neutrons versus protons, but let's take the most stable one. Okay, so then we see we have hydrogen, deuterium. Hydrogen, of course, is a free proton, so no binding energy, just one particle. We have a deuteron, we have a triton and helium-3, which is a radioactive isotope of helium, right? And then we have helium-4, that's extremely stable. To either side of helium, we go way down on one side and we go way down on the other side as well. So it's this feature in the nuclear binding energy curve that explains why alpha particles are so stable. Okay, so what that means is going back to for one moment to my bag of particles. What I really should think about is two of these and 2 protons and 2 neutrons make 1 alpha particle. And there is another alpha particle in my nucleus, right? They can rearrange and they aren't really, there permanently, but they are even inside the nucleus, inside this bag of all the nucleons, they can form entities that are there. And so now if somehow either because it's a nucleus that's not as stable as a neighboring nucleus and I can tunnel through the potential barrier and have an alpha particle shoot out, or if it's an induced decay, maybe it's because something just hits it and it just gets knocked apart. Either way, what can come out is an alpha particle because that already sticks more tightly together than a triton or a helium-3 or a lithium-6, right? And so, of course, we can also have just a single one knocked out, but we can also have this smaller bag of 4 of them knocked out, right? And so that's one feature that the mass formula explains. So we have alpha particles as one type of radiation, but we don't have, say another type of radiation where lithium-6 nuclei are emitted, right? But this is a, particularly stable beast in here. Okay, then going further up, we get to carbon, oxygen, and then the most stable nucleus, the most binding energy per nucleon is iron 56. And then getting more massive than that, we fall down the binding energy curve. And so the sun produces energy in fusion reactions, and the reason that energy is available is that the heavier nuclei that get produced in the nuclear fusion reactions in the sun have binding energy that gets released compared to the lighter constituents, right? And so going up this curve, fusion releases energy, or if you start from the heavy elements, fission also releases energy. Not as much, but we still, splitting up a uranium nucleus into whatever, thorium and whatever, then as the mass balance, you get energy released that way, or fusing, you also get binding energy released, right? If fusion is what happens in stars, then we can produce all the carbon and oxygen and so on. And so you and I are just a teaspoonful of stardust. But where do the heavier elements even come from? If they can't be produced in fusion reaction in stars, where does all the uranium come from? Does anybody know?
Supernovae.
Yeah.
Right? So violent cosmic events where energy is available from gravitational potential or other processes to, in those events, in a often very brief moment, create enormous amounts of these materials, and then they spread out, right? And then we can, mine them and concentrate them and use them in fission reactors. All right, so now we know something about this, but what about beta and gamma radiation? So where did my, hold on, sorry, one moment. Okay. Yeah, so if we look at this plot again, it's showing the number of neutrons versus the number of protons. So, and then the line n equal to z would be just the diagonal, right? And we see that, again, to compensate for the Coulomb repulsion, the heavier nuclei, the more protons I have, the more of a neutron excess I need. So for one, that leads to, when I split uranium, I actually end up with the lighter particles, about half of the number of protons as the uranium, right? It doesn't split right down the middle, so it's, you know, some random combination that adds up to the 92 protons. But it ends up, if I look at those nuclei, they have a lower neutron excess than the uranium. Even if I take two of these and combine them, that's still less than the neutron excess of uranium. And so I end up with a couple of additional neutrons. And that's how I can get the chain reaction to sustain. But also, all right, so what's the binding energy of the products that are resulting? It's, as we go up that curve, often I end up not at the ideal spot after, say, a spontaneous fission event. Okay, so I can use beta decay to basically change a neutron to a proton or change a proton to a neutron and then get closer to the line of stability. Okay, if I'm neutron rich, converting a neutron to a proton gets me closer to the line of stability from the one side. Converting a neutron to a proton, that means I'm emitting a negative charge. So that the overall charge of the system balances, right? So that I create a positive charge of the proton plus a negative charge of the electron, zero net charge in the neutron before the decay. Or I'm in a place where I have too many protons and I want to decay towards the line of stability. And then I need to convert a proton to a neutron. You may object, that's not possible. Protons have less mass than neutrons by a tiny amount. Yes, but if I get so much benefit from more binding energy release, then I can take some of that binding energy to make up for that mass difference and still end up with excess binding energy, right? So I can either have a beta minus or a beta plus decay to get closer to the line of stability. Let's look at what that looks like in the in the form of equations. So all right, let me new page. Okay, so I either want to have some let me use black. I have some nucleus X that has some number of nuclei and some number of protons, and it can, let's assume that it's neutron rich. So I basically want to convert a neutron to a proton, and then I need to balance the charge by also creating an electron. And the electron is a lepton, and so I also need to balance the lepton number +1 with an anti-neutrino, which has a lepton number of -1 and no electric charge. So all the quantum numbers, electric charge, Q is +1, Q here for the electron is -1, electric charge here is 0. For the neutron it's 0, so 0 is +1, -1, +0, check. And neutrons and protons are baryons, so they are not leptons, so they have a lepton number of 0. Lepton number also written as capital L. And so here again, the balance is 0 is 0, +1, -1, and that also works out, right? So we need to conserve all these discrete quantum numbers. So in other words, so this would happen to a free proton within about 15 minutes or so on average, or with a 15-minute half-life. That's not the average, but it can also happen inside the nuclear environment. And so I end up with the same number A, because the number of neutrons plus protons doesn't change. I end up with a Z +1 and an electron and an electron anti-neutrino. Or if I have a different nucleus, and now I assume that it's not neutron rich but proton rich instead, then it's going to convert one of those protons into a neutron, and I need to make them up for that loss in one charge. That one positive charge needs to go somewhere, and so I emit a positron. Sometimes these are also called beta plus or beta minus in this context, but they are just electrons. And then that's an antiparticle. The positron here is an antiparticle. And so I need to balance that with a particle emitted together with it. Lepton numbers -1 and lepton numbers +1 respectively. Okay, so that's a little bit of nuclear physics, these processes actually happen through not the strong but the weak nuclear force. And this diagram, for example, you would have two spectator quarks, and then one quark would emit W boson. So let's see, I had a neutron, so this would be U d, and it becomes a proton, sorry, not a W plus, a W minus, right? And that then becomes the electron and the electron anti-neutrino going forward, or I could have drawn it, a particle going forward in time is kind of the same like an antiparticle going forward is kind of like the same as particle going backward in time, right? But however you want to draw it, right? So that's the Feynman diagram for the weak decay, and instead of gluons of the strong nuclear force or the exchange mesons of the effective nuclear force, we now have W and Z bosons of the weak nuclear force mediating the weak decays that are responsible for beta decays. Okay, so this is all about beta decay, right? The previous page was all about alpha decay, really, right? And then we have one more type of radiation. And so if I have either alpha or beta decay, I oftentimes end up in a state where I end up with the, sorry, let's go here. Really, I don't usually end up in the ground state. I end up in an excited state. Also, this really is a different, this really, if this is X, then this represents a different particle, right? So I don't know, it's, right, it's a different element. But these, we also usually put an asterisk denoting that it's not in the ground state, but it's in an excited state. And so then, gamma decay is just the de-excitation from, you know, some excited state to a less excited state, right? So just the nucleons inside that bag reshuffling and emitting a photon, right? All right. So those are the main processes emitting radiation, and then we have seen with this semi-empirical mass formula also for going from high Z to low Z means also free neutrons, right? Like I've said, if we go from for example, uranium to the two daughter nuclei. Those daughter nuclei are less neutron rich, and so there are maybe 3 neutrons left over as well. And so that's where neutrons might come from. All right, so let's see, that was a lot of information, rather condensed, but did most of this make sense? What, if anything, are your questions?
And those gamma rays are just coming from like electron shell decays, just much higher energy scale.
Right. So again, just like electrons rearranging themselves in the shell, an electron de-exciting in the atom, that may emit, one light of one of the spectral lines, right? For hydrogen, there's the Balmer series Paschen, and so on, right? And similarly, in the back model, we can't really, talk about that in specifics, but I mentioned that even within the nucleus, there are these virtual alpha particles, right? So you might imagine that right after a decay, the daughter nuclei are still in some jumbled state, and then as virtual alpha particles form inside that nucleus, they may free up more binding energy, right? Something like that, or as they rearrange in the shells in tighter structures if you go to the shell model. But I really haven't talked about that. Does that answer your question?
Yeah.
All right. Okay, so we now know where radiation comes from, at least from nuclear processes. We also have all this knowledge to file away for what makes good shielding material and what doesn't. We don't really know yet how radiation interacts with matter, but what do you think, what type of material can be activated by being irradiated easily, and what material can't be activated as easily? What does activated mean? Activated means if it's exposed to radiation, it becomes radioactive itself, right? So why would material become radioactive if it's exposed to radiation?
If it gained an electron, or gained a neutron, gained a proton, gained an alpha particle, it could now be unstable, more stable than it was before it got the alpha particle, or maybe even less stable, and it would then want to decay to a lower binding energy.
Right?
Or higher binding energy.
The radiation causes interactions in the material that split or even particles may get absorbed to form different nuclei that are less stable and hence radioactive, right? Okay, so just based on that binding energy curve, not specifically, but in general terms, what do you think, where is that more likely and where is that less likely? Or did we have any diagram that that would explain how we can think about this?
The peaks on the binding energy would be more difficult, right? To be excited.
Right, they just wouldn't want to absorb anything, right? So something like iron is just not very tempted to change drastically, right? But yet there are other elements near iron. The curve is very flat there. And so we could have iron nuclei undergo reactions if I shoot an energetic particle at it. But all right, so I guess maybe this question wasn't really quite fair because we haven't done all the calculations and all the looked at it in enough detail. But basically, right, wherever, if you are on this line of stability and absorbing a particle either going one way or the other way, that wouldn't be attractive. A beta particle might not do it. But absorbing an alpha might get you somewhere off. And even if you are energetically favorable where you are at, if the particle that's coming provides the energy, there's still a possibility for it to be absorbed, right? But basically, if the more stable you are relative to particles nearby, the less likely it is that you will absorb that particle, right? So yes, basically the peaks in the curve correspond to materials that are less likely to get activated, and then so we haven't talked about cross sections and so on. So there's a bit more to it, but this should give you some first idea about what's going on, what's possibly going on. All right, so this actually took more time than I thought. I thought I could talk about galactic sources of radiation and some of the other acceleration mechanisms and the composition of cosmic rays. But I guess we'll have to postpone that or leave that to your radiation physics course. So cosmic rays, what's coming down from outer space? Well, if it hits the atmosphere, it may interact with with molecules of nitrogen or oxygen. And then you have fragments of those particles that again produce more fragments, and you end up with a large shower of exponentially more particles after every interaction until all the energy is dispersed, and you end up with a lot of muons, but also electromagnetic electrons and photons and protons, other nuclear fragments, and so on. I guess I haven't even explained what a muon is. A muon is like an electron, but a long-lived cousin of the electron. But what's coming to hit the upper atmosphere? That's mostly protons and iron nuclei. Right? Because iron nuclei are stable. If it was anything else, it could break up, but the iron nuclei are stable. It's not purely iron, there may be other components, but those are the most likely particles, right? So, and then you can look at the composition depending on what energy range you are interested in as well. So, all right. Since I'm out of time, I will stop here, but any last questions or comments? All right, then see you all on Monday. Have a good weekend.
Thank you very much.
All right, goodbye.
All right, bye.
Thank you.